All right, there we go. So section 10.2, we've already covered section 10.1, which is Lewis structure. I'm going to give you a heads up right from the start. In order for you to become proficient in VSEPR theory, so we pronounce this as VSEPR, it's valence shell electron pair repulsion. In order for you to be proficient in VSEPR theory, so section 10.2, you have to know section 10.1. Okay, you've got to be rock solid on your Lewis structures before you can progress into this section. And you know, while I still have your attention, and you always have your students' attention for the first few minutes of the lecture, remember, in a molecule, bonds are made up of pairs of electrons, and lone pairs are a pair of electrons. Even a radical is an electron, and those are all negative, right? Electrons always have a negative charge. If we have like charges, what are they going to want to do? They're going to want to repel each other, and that's why we call it valence shell electron pair. Okay, and that electron pair could come from a bond or a lone pair, and they're going to repel each other, right? They're going to, I call it quick, you could call this chapter, this section, quit crowding me, bro. Okay, you could just, or give me some room, man. Okay, back up. Okay, that's all electrons want, is they want to maximize the space between them. So let's take a look at the first bullet point. Each group of valence electrons around a central atom is located as far as possible from the others, right? Give me wide open spaces. And why do they do that? Well, there's a reason, and it's to minimize repulsions, okay? And later on, we're going to look at why water is drawn with this shape. And I'm sure many of you have seen that in other textbooks, maybe in our textbook if you've been perusing it. And we're gonna look at the rationale behind why we draw water with this bed shape, with this angle here. Anyhow, a group of electrons or a region of electron density is any number of electrons that occupies a localized region around an atom. So this red thing here, this is regions of electron density. I'm going to try to use that because it seems to be the vernacular of choice here at UCCS. I never used that until I moved here, but yeah, it seems to be really popular. And it really helps you understand, you know, a region of electron density. Well, what could that be? It could be either a single bond, a double bond, a triple bond, a lone pair, or a single electron, which is a radical. So we'll just put this here, a radical. All of those count as a region of electron density. So let me ask you a question. If I look at this water molecule, this beautiful Lewis structure that I have drawn here, could anybody tell me, based off of this bullet point right here, how many regions of electron density are there in water? Not a trick question. Might not be the easiest question on a Wednesday morning, but could anybody answer that? Absolutely. I'm very happy. I'm very pleased to see that the two students who answered are both correct. Okay, now if you're not following them, look, a region of electron density, a red, okay, it could either be a single bond. How many single bonds are there in water? There's 1, 2 single bonds. There's no double bond. There's no triple bond. There's no radical in water, but there are 2 lone pairs. So that makes a total of what? 1, 2, 3, 4 regions of electron density. Can I try another one with you? Let me try one more, just so you guys, since you guys nailed that one pretty quick. What if we draw the Lewis structure of CO2? Okay, so here's the Lewis structure of CO2. Now, I'm just talking about the central atom, right? I'm talking about the carbon. Can anybody tell me how many regions of electron density are there on carbon, on that atom, around an atom? How many regions of electron density on carbon? Not a trick question. Okay. And nobody's got it yet. Okay, good. Somebody's got it now. So I'm talking about what's bound to carbon. Okay, there are 2 regions of electron density on carbon, right? I think some people were thinking about these lone pairs. These lone pairs aren't attached to carbon, right? Those have nothing to do with carbon, those lone pairs. What are the regions of electron density on carbon? All there are 2 double bonds, right? One double bond here, and one double bond here. And so the carbon in carbon dioxide in CO2 has 2 regions of electron density. Okay, because later on we're going to look at molecular geometry. Okay, and hopefully this will become even more clear as we progress through the chapter. Now, there's a really fun exercise you can do. In fact, if you've taken, or if you're taking the online lab, I can't remember. I do too many labs, you guys. Anyhow, there's a lab that I've taught in recent memory where I've got the students to do this exercise. And you're like, well, that just looks like somebody messing around with party balloons. You're darn right it does, okay? And it actually is a really good way to represent regions of electron density and to help to understand the shapes, okay, that molecules take on based on their regions of electron density. And if you're saying like, well, what are you talking about, Mr. Dion? Well, let me explain, okay? That's why I'm here, okay? If we have two regions of electron density, right, 1, 2 like that, around a central atom. So the central atom is the atom that's in red. What's the geometry going to be? Well, if we know that there's, let's say there's 2 electrons in a bond here and 2 electrons in a bond here, how are those electrons going to get as far away from each other as possible? They are going to adopt a linear arrangement, right? The bond angle is going to be 180 degrees between those 2 bonds, okay? Now think about it. If you have your 2 arms, what's the farthest you can get your 2 arms apart from one another is to stretch them straight out, okay? You don't put them at a 90-degree angle. You can get them farther apart than that. And so give me a thumbs up if you just understand the first shape, linear shape, 2 regions of electron density. They're going to want to get as far away from each other as possible. Yeah, great. Okay, cool. Awesome. That's wonderful. Well, let's move on to the next shape, which is when we have 1, 2, 3 regions of electron density like that. Usually this one isn't that much of a stretch for students either because they just think, well, come on, Mr. Dion, if you have a triangle, right? If you have 3 points, you know, the farthest you can get them apart is in a triangle like that, and all the bond angles are going to be 120 degrees. Okay, so all the bond angles are going to be 120 degrees. I don't know. This would be a pretty tough demo to do, but maybe if I, you know, stood on 1 foot and said, okay, I want to take my other leg and my 2 arms and get them as far apart from each other as possible, right? They'd have to adopt some kind of triangular arrangement. Maybe that's kind of a silly explanation, but give me a thumbs up if you follow me on trigonal, what we call a trigonal planar. And the reason we call it planar is because it's all in a plane. Yeah, again, not that bad. Students usually don't struggle with trigonal planar. Again, I want to point out that the planar means that it's flat, right? You can lay all 3 of those balloons on top of a table and they would all be touching it. Now, the next one is not nearly as much, or is not nearly as intuitive, in my opinion. Okay, if I have 4 points and I want to get them as far away from each other, okay, if I have 1, 2, 3, 4 points like this, okay, so I'll put them as little black dots here, okay. I've taught this class long enough to know, and it's hard for me to gauge your, you know, your facial expression over Microsoft Teams, but I've taught this class long enough to know that there's always a few people who think, well, it's going to be a square, right? If I put them in a square, then they're all 90 degrees from each other, right? This bond angle here, this would be 90 degrees, right? This would be 90 degrees, this is 90, right? That's as far away as you can get 4 points from each other. Well, I'm here to tell you that that is not true, okay? Now let me just try something here. There we go. And I'm going to go to my camera so you can see my model. And this is actually the answer. Okay, if I have a central atom, see how I have a central atom, which is the black sphere, and then I have 4 white spheres surrounding it. You can see that that is not a square shape. Okay, that is not a square shape. In fact, if I put it in the palm of my hand, well, it's kind of hard to do and get a good, it's hard to get some good angles here for you. But anyhow, if I put it in the palm of my hand, that is not a square. All right, does anybody know the name of that shape? It's on the last slide. Could anybody tell me what the name of this shape is? Sorry, I'm going to try to scroll down here while I'm explaining at the same time. This has got a name. This shape has a name. Yeah, we call this a tetrahedron, okay? So this is a tetrahedron. It's not a prism, it's a tetrahedron, and we say the shape is tetrahedral, okay? Now the next thing, so you have to know what a tetrahedron is. You bet your bobby socks you do. Now the next thing is about the bond angles. The bond angles between these 2 atoms or these 2 atoms or these 2 atoms or any 2 atoms in this molecule is a really interesting number. It's 109.5 degrees, okay? So 109.5 degrees in the tetrahedron. Let me go back to my screen sharing here. I just want to double check before I keep yammering on here. Can my students see my screen? My wonderful students who are paying attention. There's all of you, I know. Great. Okay, good. So the tetrahedron, yeah, not as intuitive. Okay, definitely not as intuitive. But again, if we see that we have 1, 2, 3, 4 of regions of electron density, excuse me, they spread out and they make that bond angle of 109.5 degrees. Okay, and that's called the tetrahedral shape, and that's when we have 4 electron groups. Remember, electron group is the same thing as as region of electron density. Okay, you could write that in here. So electron groups means the same thing as reds. It's going a little too fast here for his brain. There we go. All right. Oops, there we go. All right. The next one is another really interesting shape. And that is if we have 5 regions of electron density all around a single point. Okay, so we have 1, you can see it buried there in the back, 2, 3, 4, 5 regions like that. We make what's called the Trigonal Bipyramidal. Okay, the Trigonal Bipyramidal shape. And we have 2 different bond angles in the Trigonal Bipyramidal shape. In fact, it's the only one of these shapes that has 2 bond angles, because you'll see the next one only has 1, which is 90 degrees, and we'll get there in a second. But anyhow, I made a Trigonal Bipyramid with my beautiful model kit, so let me just show you what it looks like. You know, maybe me waving it around will help you grasp it a little bit. Can you all see my camera? Sorry, I'm just not used to switching around this much. Can everybody see my model? Yeah, okay, great. Thanks, Emma. Thanks, Joel, Aaron, gang. Great. Okay, so here we go. Here's my Trigonal Bipyramid. What's kind of cool is if you look at it down this axis, like this, you can only see 5 of the atoms. You can't see the atom that I'm holding. But anyhow, here's the Trigonal Bipyramid. So if I hold it like this, you can see how there's a triangle, right? It kind of looks like Trigonal Planar, these 3 atoms here. But then if you focus on these 2 atoms here, they're in a straight line, right? It's linear. So you kind of get like 2 shapes at once here. And if you've ever studied AP chemistry before, which I think a few students have, if you're wondering, you know, when will you get to the seesaw and the T-shape and all this stuff, Mr. Dean, we'll talk about that later, okay? Right now we're going to focus on all the bonds being filled up, and we're not going to obsess about lone pairs quite yet. But anyhow, you see that there's 2 bond angles here. There's the bond angle of 120 degrees between all the atoms that are in the center, what we call the center. And then we have a bond angle of 90 degrees. There we go. You can see a bond angle of 90 degrees between what these are called the the axial atoms and the equatorial, right? Because the equatorial ones are on the equator. Anyhow, give me a thumbs up if you follow my model, if it helps a little bit. Does this help at all? Do I need to show these models? Even if it's one person that benefits from it, I'm going to do it, okay? Okay, cool. Okay, it helps a lot. Good. All right. I kind of assume that not everybody has a model kit at home. I would be, unfortunately, after all that rambling, I don't have a model of the octahedron. Okay, I don't have a model that has any atoms with 6 holes so that you can see the octahedron. But anyhow, excuse me, you could try to make the octahedron at home. I'm sure many of you have homes where there might be some party balloons kicking around. You know, it's too bad it's university and there's no extra credit for anything. But if there was, you know, I'd tell you to make these models, take a picture of them, send it to me. I'd give you a point, but sorry, I can't. Otherwise, I could get in trouble for doing stuff like that. Anyhow, it might be something fun to try. Would anybody be willing to try, just for fun? Take a picture, send it to I could show it in class maybe or something for the whole group. Anyhow, you could try doing this. So if you take 6 balloons and tie them all together, they kind of adopt this shape where every single every single bond angle is 90 degrees. Look at this. So this is a 90-degree bond angle. This is a 90-degree angle like that. So they're all octahedral, 90 degrees, and we call that the octahedral shape, where we have 6 regions of electron density. Okay, you've got to be fully aware of all of these shapes, and trust me, if you practice, you're going to master these. Okay, you definitely will if you put in the time. Okay, now what's the take-home message from this slide? You know, if I was talking to somebody on the street, I mean, that's what I do. teacher. You know, I just walk up to people on the street and start talking about chemistry. It's a good way to make a lot of friends. Anyway, what's the whole take-home point behind this slide? Is that these balloons or atoms that are in these molecules, when they're attached to a central point, okay, this red sphere in all of them, okay, when they're attached to a central point, what do? They seek to maximize the space between them. Give me a thumbs up if you follow me on that rationale, right? Girls just want to have fun, and electrons just need space, okay? They just want to get the heck away from each other. Thank you, Sierra. That's wonderful. Okay. All right, there we go. Let me just scroll down here. Okay, perfecto. Well, let's talk a little bit more about molecular shape, because I'll just warn you ahead of time that there's more shapes than those 5. Okay, there's several other shapes that we have to be aware of, and we're going to talk about them today. So it says here, electron group arrangement versus molecular shape. The electron group arrangement, or what sometimes I'll just call it the electron arrangement, is defined by both bonding and non-bonding electron groups. Okay, I can't stress this enough. You really have to know this definition. Okay, so again, electron group arrangement means both bonding. That means a single bond, a double bond, or a triple bond, and non-bonding. What's non-bonding? A lone pair or a radical. Okay, whereas molecular shape, or what Mr. Dion will usually just refer to as molecular geometry, because that's what I grew up with, is the three-dimensional arrangement of nuclei joined by the bonding groups. Okay, so the bonds only. Look, if you could just make sure to pay attention to this. This is really important, because I'm going to mention electron arrangement, or sometimes, you know what, sometimes I'll call this electron geometry. Let me write that in, okay? Sometimes I'll just call this electron geometry, because that's the shape the electrons are taking. And a lot of times I will just call this molecular geometry, like that, because it is the shape that refers to only the bonding groups. Okay, so that means we leave out the lone pairs. All right. Excuse me. Molecular shape is classified using the following designation. So we have A next to X, which is our atoms, subscript M for the number of atoms that we have, next to E, and E is for non-bonding valence electron group. Look, I'll put it more politically correct, or maybe less politically correct. This means lone pairs, okay? The number of lone pairs. We're not going to look at a whole heck of a lot of radicals, okay, in molecular geometry. Maybe a few, but not many. Very, very few. Okay, again, electron geometry, that refers to bonds and lone pairs. Molecular geometry, leave out the lone pairs. Just focus on the bonds. Okay, with that in mind, let's move forward. Let's talk a little bit more about bond angles. And we already started talking about the bond angle in linear, trigonal planar, tetrahedral, square bipyramidal, or sorry, trigonal bipyramidal rather, and octahedral. Anyhow, so bond angle is the angle formed by the nuclei of two surrounding atoms with the nucleus of a central atom. So you've got to have 3 atoms to make a bond angle, right? If you look at the Lewis structure of carbon dioxide, CO2, okay, like this, there is a bond angle in here, and the bond angle is 180 degrees. This is a linear molecule. There is no bond angle associated with either oxygen, right? They don't have a bond angle. How could they have an angle? They're only attached to one thing, right? If I look at the molecule HF or HCl, let's say, okay, there's no bond angle here. You might say, okay, well, this looks like a straight line, Mr. Dion, that's linear. Well, all bonds are drawn as straight lines, okay? There's no bond angles. It says formed by the nuclei of 2 surrounding atoms with the nucleus of a central atom. So that means you've got to have a minimum of 3, okay? And so the example that's shown here is showing a trigonal planar, and so the bond angle would be equal to 120 degrees, and we discussed that. Now, that bond angle is called an ideal bond angle, right? If you take a circle and divide it 360 degrees and you divide that by 3, what do you get? 120. Okay, that's an ideal bond angle. Real bond angles will almost always deviate from the ideal value in many cases. So what does that mean? What that means is that when chemists or physicists, when they measure actual bond angles in actual molecules, it's very rare that they're going to be exactly, 120, exactly 109.5. Of course, there are cases where it's like that, but rarely, okay? Now, if we have a central atom, shown down here on the bottom left, okay, where that central atom is attached to 3 atoms and they're all identical, right? We have X, X, and X. They're all the same. Well, in that case, the bond angle probably would be exactly 120 degrees. But if you look at the next 3 examples, it says that in all 3 of these scenarios, the ideal angle is not going to be the same as reality. Okay, so what it's saying is none of these bond angles are going to be exactly 120 degrees. Why in the first case? Well, the reason why it's not going to be identical in the first case is because here we have a double bond, okay? More electron density, okay? So it's going to repel these single bonds down a little bit more probably. The next one is, what if we have a different atom, right? What if we have a different atom that is bigger, just takes up more space? Well, that's going to have repulsion on those 2 atoms, the X atoms, and so that will change the bond angles or get them to not be completely ideal. What if we have a lone pair? Well, a lone pair isn't a bond, okay? So the only time that the real bond angle is going to be exactly equal to the ideal is usually when everything is all perfectly symmetrical, okay? And we'll look at, and if you're thinking, oh, we'll never look at exceptions to that, okay, we'll look at many exceptions to that along the way. Now, there's always somebody who's always thinking about the worst case scenario, not you guys, of course. But if you're thinking, oh no, does that mean I have to memorize thousands of bond angles? Of course not. Of course not. As long as you understand the crux of what's going on, you'll be in pretty good shape. Okay, so let's get back to our linear molecule. Show some examples here. The bond angle in linear is 180 degrees. We've gone over this already. One of the examples that they put in here is carbon disulphide, CS2. I'll throw something else in the ring here, which would be CO2. Okay, so carbon dioxide is a linear molecule. And I showed you that earlier on. If we draw the Lewis structure of CO2, right, the carbon has 2 regions of electron density, the 2 double bonds. What's the furthest they can get away from each other is going to be 180 degrees. Let me show you what the model of CO2 looks like from my model kit quickly. You're going to like this. Okay, where's my camera? You guys see my model? So this is CO2, the 2 double bonds. And you see how I had to bend these plastic pieces to get it like that? Okay, you can see it. Cool. All right, just let me scroll down so I can see what you're typing here. Okay, anyhow, but if you look at it down this axis, it's a straight line. Okay, it's perfectly linear. Okay, even though it's got those big double bonds. And you see how they're perpendicular to each other. And we're not talking about that today, anyhow. Mr. Dion always likes to talk about everything, but anyhow, kind of cool, huh? So there's a carbon dioxide molecule to show you. Where was I? Good. Get back to slides here. Good. All right. So carbon disulphide, that's CS2. HCN, which is hydrogen hydrogen cyanide. So HCN, like this. There's the Lewis structure. The bond angle here is 180 degrees, right? We have 2 reds, 2 regions of electron density. They don't have to be identical to each other. They can be very different from one another. Oops, didn't mean to do that. Where was I? Oh, coronavirus, go away. Where was I? Here we are. Yeah, you can see the bond angle here is 180 degrees, even though we've got a single bond and a triple bond. They still count as 2 regions of electron density, right? 2 reds, 2 regions of electron density like that. Anyhow, it's the kind of thing I could probably yammer on for a while. But let's move on to the next shape, which was what? The trigonal planar. Okay, they've given us some examples here. And the examples that they chose are things like sulfur trioxide, boron trifluoride. Let me just draw one of them, which is Pf3, okay, because that's shown right here, Pf3. And we talked about why boron is an exception. It only forms 3 bonds, so it has an incomplete octet. Anyway, we draw our Lewis structure like that, and you can clearly see that the bond angle since all of those atoms are identical, it's going to be 120 degrees. Now, here's where I really want to draw your attention, is down here. You probably notice, like, wait a second, that's not trigonal planar. That says bent. Yeah. If we have one of these molecules, I'll just pick one at random. Let's choose lead 2 chloride, so PbCl2. If we draw the Lewis structure of PbCl2, okay, let's give it a try here. Maybe I'll do it like that on the side of the page. Okay, so PbCl2, phosphorus is in group 5a. It's got 5 valence electrons. Chlorine is in group 7a. It's got 7 valence electrons. So we've got 5 plus 14. Am I missing an electron here? Am I in the right group? No, I'm not. Jeepers, Mr. Dion, you need to wake up. Yeah, phosphorus is in group 5, Mr. Dion, you bozo. Okay, it's not phosphorus, it's lead. Like, this doesn't add up. Anyhow, so lead is in group 4A. So we have 4 plus 14, which equals 18 valence electrons. There we go. Sorry about that. Anyhow, if we draw the Lewis structure of PbCl2, okay, if you drew this, if I was in class with you guys right now in Centennial Hall, okay, and if I said to you, I want you to draw me the Lewis structure of PbCl2, and if somebody in the class, okay, if somebody in the class had drawn this, I would have gone up to them and said, hey, 100%, nothing wrong with that Lewis structure. I'll give that double check mark. There's nothing wrong with that Lewis structure at all. But let me ask you another question. How many regions of electron density are there around that lead atom? There's 1, 2, 3, right? We have 2 single bonds and a lone pair. So 3 regions of electron density, 3 reds. How are those 3 groups going to get away from each other as far as possible? Let me show you. Here's what we do. We say they're going to have angles close to 120 degrees, right? They're going to try to adopt that trigonal planar arrangement. So I'm going to put the 2 chlorines down like this. Now, there's a few ways that you're going to see the lone pair drawn. Some people draw it like this. I will do that a lot because I'm an organic chemist, and that's how organic chemists generally do it. Sometimes you'll see this. You'll see them draw a bond like that, and then they'll put the lone pair at the end of it like that. That is probably what I'll use a lot of the times in class because I find it really helpful, you know, for students to see very clearly that, hey, you know, there's 1, 2, 3 regions of electron density. Another option, okay, and I promise this is the last one. The last option is sometimes you'll see it drawn like this, where they'll draw an orbital, you know, like this, and then they'll put the lone pair in the orbital, and then you still can see that there's 1, 2, 3 regions of electron density. All are perfectly acceptable, but let's get back to, I want to just draw the stick there, the line, with the lone pair at the end. Okay, how many regions of electron density do we have? I've said this like 6 times already. There are 3 of them. So that means that lone pair and those 2 bonds are going to try to get as far away from each other as possible. Now, the question is the bond angle going to be exactly 120 degrees? Probably not. It probably won't be. And in terms of electron geometry and molecular geometry, we need to clarify that, what it is. So I'm talking about PbCl2. Could anybody tell me what the electron geometry is based off of what I told you maybe 3 slides ago or something? What would the electron geometry be? Not a trick question, but you might have to look back in your notes. Anybody have the electron geometry? Yes, there we go. The electron geometry is trigonal planar, right? Because electron geometry considers bonds and lone pairs. Could anybody tell me what the molecular geometry is? Well, I'll help you out. It's bent. Okay, this is a new shape. We call this the bent shape because it's bent, right? You can see how the atoms have this kind of bent shape like that. So sometimes we call it V-shaped. I will always call it bent because it's just what I'm used to. Okay, like that. Now, I'm sure there's somebody who's wondering, you know, what's the bond angle here, Mr. Dion? Well, if you have a lone pair, remember, these electrons here are not shared, and so they're going to have more, since they're not shared, there's going to be more negative charge here than there would be in these 2 bonds. And so what they will do is they will actually repel these 2 bonds down a little bit, and this bond angle will be a little less than 120 degrees, okay? Now, if you're wondering, is it 118? Is it 117? Is it 116.23? I don't know. Okay. For now, just saying little less than 120 degrees is good enough for this class. Okay. So electron geometry and molecular geometry. Let's move on from there. I'm going to go a little faster as we progress. Non-bonding lone pairs. A lone pair, as I just said, repels bonding pairs more strongly than bonding pairs, and then this decreases the bond angle. For example, if you look at the actual bond angle in tin 2 chloride, so this is the Lewis structure of tin 2 chloride, SnCl2, that measured bond angle is way less than 120 degrees. Why? Because of the repulsion by this lone pair, right? They're not shared. Okay, so they're going to be able to push these electrons down this way and squeeze that bond angle a little bit more. What else can affect bond angle? A double bond. A double bond has more electrons, right? 2 bonds, more electrons. So greater electron density than a single bond, and therefore is going to repel the single bond electrons more than they repel each other. This molecule that's shown down here, this is formaldehyde. Formaldehyde, okay. That's this molecule here. And again, you see that there's a double bond between the carbon and the oxygen, and that's going to push these bonds a little bit. It's going to squeeze them a little bit more. So the bond angle here is going to be a little bigger, 122. This bond angle is going to be a little smaller. Okay? Even though the ideal bond angle is 120 degrees, for both of these, for all of these bond angles shown on this entire slide, you can see how electron density can affect those bond angles. I know I haven't asked you a lot of questions yet, but give me a thumbs up if you follow me on the concept. Don't worry, we will try some problems, but we just have to go through all the shapes. It always takes a little while to go through all the shapes before we can really, kind of just get into problem. Well, let's look at the tetrahedron electron geometry or electron group arrangement. I'm going to go over this one a little bit quicker. But if we have the tetrahedron, we know that the bond angles are all going to be close to 109.5. If I remove one of those groups, right? If I were to take this group and remove it, then and replace it with a lone pair, like this, then I have a new shape that's called Trigonal Pyramidal. And if I was to remove another group, then I replace it with 2 lone pairs, then I get another bent shape. Let me show you what the heck is going on here. Okay, this is where the model might come in handy. Done a lot of switching the old screen around today, huh? Anyhow, let me get back to you and show you my model of the tetrahedron. Where is it? Where's my tetrahedron? Here it is. Okay. Here's the tetrahedron. Okay. Okay. If I remove one of those atoms, okay, let me remove one. So this is the tetrahedron. All the bond angles are 109.5. Okay, she's a beaut. Okay, if I remove one of those atoms, and when I do that, I want you to assume that when I have a stick here by itself, we're going to assume that that's just a lone pair. Now, what's the shape? You can see that it's trigonal, right? All 3 of these white atoms are 120. They look like they're 120 degrees apart, but they're not. Okay, they're closer to 109.5 because of the repulsion of this lone pair, right? It's squeezing these. Look at that demo, huh? It's squeezing them down a little bit. Now, you can also see that it's trigonal, but it's also a pyramid. You see how it's up on my hand like that, like a tripod, like that? So we call that the Trigonal Pyramidal molecular geometry. Okay, the electron geometry here is still tetrahedral, but the molecular geometry only considers something that starts with B and ends with ons. That's right, bonds. Okay, so there we go. Give me a thumbs up if you follow me on Trigonal Pyramidal. I'm holding this thing the best I can. Okay. All right, good. Okay, so if I remove one more atom, okay, if I remove one more atom like this, my electron geometry, which considers bonds and the 2 lone pairs, is still tetrahedral. But what's my shape? It's just bent. Okay, I have a bent shape like that. Okay, what is oxygen in water? What does it have? It's got 2 single bonds and 2 lone pairs. And that's why water is always drawn with that little bond angle, okay? Because water's molecular geometry is bent, okay? Now, what about the bond angles in this trigonal pyramid and in this bent shape here? Let's take a look. The bond angles, which aren't covered on this slide, but I'm going to go over them with you. Just let me erase all of the spinach that I put on here, okay? The bond angle in the tetrahedron, again, is 109.5, okay, 109.5 degrees. The bond angle here in the trigonal pyramid, all you have to say is less than 109.5 degrees, right? Because of the repulsion due to the lone pair, squeezing those bonds together a little tighter. Similarly, in the bent structure here, and I'm going to do my best here, okay, this bond angle would also be less than 109.5. Okay, in fact, in water, it's close to 104 degrees, right? In ammonia, which is trigonal pyramidal, the bond angle is close to 107 degrees. Mr. Dion, do I have to memorize all of those bond angles? No, okay? As long as you say less than 109.5, that will be close enough, okay? Give me a thumbs up if you just follow me on the rationale, because if you do thus far, then the trigonal bipyramidal will be should be pretty straightforward. Okay, great, wonderful. Well, let's move on from there and talk about the trigonal bipyramidal. We got a whole holy host of shapes here, don't we, you guys? We've got the trigonal bipyramid. Okay, if you remove one of those groups, okay, remember I told you the ones on the ends, those are called the axial position. So these are axial. The ones around the middle, these are called the equatorial positions. When you start ripping atoms off of the trigonal bipyramid, you only rip them off from the equatorial position. Okay, you never rip them off from the axial position. Again, the bond angles that we looked at earlier this morning were 90 degrees here and then 120 degrees here. I'm not going to reteach that. If you remove one of those atoms and replace it with a lone pair, you get what's called a seesaw. If you remove two of them, you get what's called a T-shape. And if you remove three of them, then you get something that's linear. Let me go back to my camera. Show you. Where am I? There we go. Here's my trigonal bipyramid. Okay, hold on to your hats, people. Here we go. Trigonal bipyramid, bond angle between axial and equatorial, 90 degrees. Bond angle between all equatorials, 120 degrees. Okay, if I rip off one of the atoms like this, my electron geometry is still trigonal bipyramidal, but my molecular geometry is seesaw. You want to see this? Hold on. Son of a gun. Stupid iPad. Okay, there we go. Can you see the seesaw? Son of a gun. I'm trying to make it seesaw for you. Can anybody see that? Oh, COVID-19 teaching. You are just the bomb diggy. Okay? I'm really trying to show you. Maybe if I hold it like this, right? You can imagine it on a playground. Right? Seesaws always have some kind of sound effects and kind of squeak or something. Does anybody follow me on this? Yes, haha. Okay, I'll take it. Emma, good. Okay, I'll take it. Okay, so that's the seesaw shape. If I rip off one more, then I get the T shape. The T shape's a lot easier for me to show you, okay? It looks like the letter T. Again, you can see the electron geometry is still trigonal bipyramidal, but now you can clearly see the T shape like that. The bond angles here are 90. The bond angle here is supposed to be 180, but of course it's going to be pushed in a little bit like this because these are going to be repelling, right? And then if I pull off one more, I get linear, okay? There you go. Can you see it? So again, my electron geometry is still trigonal bipyramidal, but I have a linear molecule. Who thinks this is cool? Just me? All right. I hope the models help you. I'm sorry that you can't. I don't think you can go to the Science Center and just grab a model kit off the shelf anymore. You used to be able to. Now, where was I? Y'all. Oops. No, did I do that incorrectly? I think I did. All right. Super cool. Yeah, I think it's super cool too. I really enjoy molecular geometry. I know I say that about every chapter, but I think the molecular geometry is pretty on the up and up. Okay, so axial and equatorial positions. I went over those with you and explained to you what axial and equatorial positions are. All you really need to know is that the equatorial repulsions are weaker than the axial equatorial repulsions. And so when we start ripping off groups, we always take the equatorials first. We went over that. What else? Hey, the octahedron. I'm sorry, you guys, I really don't have an octahedral atom in my whole entire kit. I can double check, but I looked this morning. Yeah, there's nothing that has six spots in it. Sorry about that. Anyhow, so if you followed me on those, though, you'll just have to imagine these a little bit. If you have the octahedron, I mean, all of the positions are equivalent. There's no axial or equatorial position. So if I remove one of those groups, right, if I remove one of those atoms and I replace it, maybe I should have circled this one here, and I replace it with a lone pair, I get what's called square pyramidal. Sometimes you'll hear that called square-based pyramidal or square pyramidal. Either one works. And then finally, a lot of students love this shape, is if you remove two groups like this, they're going to be opposite of each other, right? To make two lone pairs that are going to be as far away from each other as possible, you get what's called square planar. Okay, square planar. Now that's the last shape, I believe, that we're going to look at this morning. And you're probably thinking, man, that's a lot of shapes. That's a lot of shapes. Okay, it is a lot of shapes. But again, if we practice and practice, you'll get stronger and stronger at all of these shapes. And of course, we're going to look at some examples. So that's where I want to get to. But before we do that, I just want to remind you of a rule that I already taught you about earlier on in this class. I think maybe the last two lectures, I think I mentioned it on Friday and on Monday, which is that when we're dealing with elements that are in the second period, they cannot exceed the octet rule. Okay, so we can only have a maximum of 4 bonds. Whereas once we get into central atoms that come in the third period and below, so from the periods 3 to 6, then we can have, you know, more than 4 bonds, right? We can exceed the octet rule, okay? So these are all examples of where the octet rule is exceeded. But you know what? You guys learned that when we did Lewis structures, okay? So we've already really looked at that in detail. The next slide, I feel, is a little bit of repetition. It's just a table that's put together by Dr. Silverberg in the book. If it helps you, I have another table that I'm going to show you in a couple of slides to just rationalize, you know, molecular geometry, electron geometry, bond angles, the names of the shapes, because let's face it, it's not easy to remember them all. And this is 3 reds that we looked at, 2, 3, and 4 reds around the central atom. Let's see here, the 4 steps for converting a molecular formula to a molecular shape. I mean, you can use this if you want. It's a guideline, again, put forth by Dr. Silverberg in the textbook. Look, Mr. Dion's way is just draw yourself a good Lewis structure and then just maximize the distance between everything, okay? As possible. I find that trying to just memorize tables is doable. I suppose I have them memorized at this point in my life, but a solid understanding when you're first getting going on the Lewis structures and the molecular geometries will really take you where you want to go. So with that in mind, I'm sure you're sick of hearing me talk. Let's try a practice problem. Let's start with, oops, I didn't mean to do that. Let's start with what? Let's start with Pf3, so phosphorus trifluoride. And it says here, draw the molecular shape, predict the bond angle relative to ideal angle. So, you know, relative to ideal angles, all that means is good enough, okay? Something that's acceptable. Again, Mr. Dion is not insane, okay? Not that insane. He doesn't expect you to memorize every bond angle under the sun. So let's get started and draw the Lewis structure of Pf3. Let me give you a second to try and draw it yourself. Hopefully you have a pencil and a piece of scratch paper. Just give it a shot. If you're at a restaurant, just grab a napkin and French fries and ketchup and start drawing. If anybody wants to take a picture of what they have and put it in the chat of their Lewis structure, that's cool too. The reason I mentioned the restaurant is because last night I was teaching a class and you could actually hear the student turn their microphone on by accident. The student didn't mean to do it, but I could hear them get into their car, start it up, and drive somewhere when they were listening to a lecture. It was funny. Okay, yeah, so let's get started with Pf3, phosphorus trifluoride. So Pf3, phosphorus is in group 5A, got 5 valence electrons. Fluorine is in group 7A, it's got 7 valence electrons times 3, so that's 21 plus 5 equals a total of 26 electrons. Look, we know that fluorine can only ever have one bond and 3 lone pairs. So we're going to start like this. Okay, I'm going to start like this. That's 8 times 3, which is 24. I've got 2 electrons left over. This is my Lewis structure. Lewis structure. And there is nothing wrong with this Lewis structure at all. Thanks, Liv. That's perfect. Beautiful, beautiful Lewis structure. Nicer than mine. Okay. Now I've got a question for you guys. Okay? If we focus on this phosphorus, I want you to tell me how many regions of electron density are there around the phosphorus atom? How many regions of electron density? Thanks, Brittany. Yeah, absolutely. Violet, yes. Lindsay, Tanner, Emma, everybody's correct. Yeah, there's 4 regions of electron density. 1, 2, 3, 4. Now, if we have 4 regions of electron density, that tells us that the electron geometry will be tetrahedral. And so we're going to do this. We're going to say, I'm going to have the lone pair pointing up like this. The way that we draw a tetrahedron is that we always draw 2 regions of electron density in the plane of the board or the plane of the page. Okay, so this bond that I've drawn here and this bond here, those are flat on the piece of paper. Now, to draw the tetrahedron properly, one of the bonds is going to have to be going behind the page like this. And for that, we use a dash. Okay, we call this a dash. And this is going behind the page. Okay, like that. Okay. And then to draw a bond that's coming out towards us, we draw what's called a wedge. 6, okay? We call this a wedge. And this is coming out of the page, Okay? Now that is a perfectly legitimate electron geometry represented here. I'm just going to try to select all this without selecting those red arrows that I drew. Here we go. Let's take this. We're going to copy it. Then we're going to paste it here again. Now, I want you to tell me, even though my electron geometry is tetrahedral, who could tell me what my molecular geometry is in phosphorus trifluoride? If you have to look back at your notes, by all means, do so. If you have to look at the book, do it. Yes, Trigonal Pyramidal. That's it. That's absolutely correct. It's Trigonal Pyramidal. Like that. Yeah. Who thinks they could do this with a little bit of practice? If you think you could do this with no practice, I'd be like, wow, that's impressive. Okay. Everybody needs practice on this. Okay. It takes a while to get used to it. Good. Let's try B, which is, you're going to laugh at the name of this molecule, COCl2. This is called phosgene. Okay, you're like, there's no phosphorus in phosgene. I know. I didn't name it. It's just the name of the molecule. Phosgene was used in chemical warfare, I think in the First World War, but it was pretty dangerous, as is all gases that are used in chemical warfare, I suppose. But the problem is that, in World War I think that they just used the wind, to push the chemical across the battlefield. And so if the wind shifted, if the wind started blowing back in your face, you're in big trouble. Anyhow, let's see. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. Chlorine has 7 valence electrons. There's 2 of them, so that's 14 plus 6 is 20. Plus 4 is 24 electrons, like that. What else do we know? We know that carbon always has 4 bonds. We know that oxygen always has 2 bonds and 2 lone pairs. And that chlorine almost always has 1 bond and 3 lone pairs, right? That's stuff that we looked at last lecture or a couple of lectures ago. So I'm going to go over this one a little bit quicker. Okay, so if I start drawing, something like this with my 3 atoms, okay, I'm going to fill up the octets like this, like that, okay? I've used up all 24 electrons, but there's a problem here. Can anybody tell me what the problem is with this structure that I've drawn? It's not a trick question. There is a problem here. Houston, we have a problem with this Lewis structure. You need chemistry 1401 to figure it out. Yes, absolutely. Well, it just so happens I have the best students in the university, and they just told me that, you know, you need a double bond here, right? Yeah, somebody says carbon needs 4 bonds. Somebody else said, what else? Somebody says the carbon doesn't have an octet. Somebody else said the oxygen needs a double bond. The oxygen doesn't have an octet. You're all right, right? You all are understanding the exact same darn thing. That carbon didn't have an octet. Oxygen didn't have an octet. And there we go. Let's move on to the next question, you guys. How many regions of electron density are around that carbon atom? How many reds are there associated with that carbon atom? 3. The answer is 3, right? Because a red, a region of electron density, okay? A single bond counts as 1 region of electron density. A double bond counts as 1 region of electron density. A triple bond counts as 1 region of electron density. A lone pair counts as 1 region of electron density. A radical counts as 1 region of electron density. And so we have 1 region of electron density here, 1 here, and 1 here. So that's a total of 3 regions of electron density. And therefore, when we have 3 regions of electron density, they're going to try, at least try, to adopt a trigonal planar arrangement. Now, what did we learn a couple of slides ago? Is that there's more electron density in a double bond than the 2 single bonds. So what's that going to do? That's going to push, right? And what these arrows are showing, you're like, what are those arrows for, Mr. Dion? They're just showing the bonds in the chlorine are going to be pushed together a little bit, okay? They're going to be pushed down like this, okay? And so this bond angle is going to be less than 120 degrees. If that bond angle is less than 120 degrees, hopefully you can do the mental math to figure out that these 2 bond angles are going to be, they're going to be greater than 120 degrees, right? This is going to be greater than 120 degrees like that. Let me show you a quick model of phosgene. And I know I'm stopping a lot, but I think that models really help. And I don't have it made, but I can make it here in a jiffy. There we go. So here is a model of phosgene. Where are my students? Okay, here we go. So here's a carbon. These are the 2 chlorines. These white ones are the chlorines. Here's the oxygen like this. There's the double bond. Again, that double bond, right? If I look at it the way that my model, these bond angles are 120, but what this double bond does is it's going to push these 2 atoms, it's going to push them a little closer together and close up that bond angle. Not much, but a little bit, okay? That we'll just say the bond angle is less than 120 degrees, and then this bond angle and this bond angle are going to be greater than 120 degrees. Is that beautiful or what? All right, take that. Take it to the bank. Okay, students. All right. Give me a thumbs up if you follow me on COCL2. Phosgene. Okay. There we go. Great. Wonderful. Well, let's move on from there. And I think, don't quote me on this. My students love to quote me on things like to get me caught, you know, between a rock and a hard place. Not you guys, of course, but anyhow, I think that on the next exam, I'll give you some iteration of this table that I'm showing you right here. And if you're thinking, now, what iteration are you going to give me, Mr. Dion? Let me see here. I've forgotten, to be frank. You know, between OChem and GenChem, I can't remember what I give on what. Let me just scroll down here quickly and see if I can figure it out here. For exam 2, I think. Sorry, guys, just bear with me 1 second. I'm just looking at something on Canvas that only I can see. And it's not loading up. So yeah, I think I give you some iteration of this. And what I think I do is that I leave out, where is it, exam 2? Yeah, anyhow, yeah, I'll give you this table. I'll give you this table that's shown right here, okay? Now, if you're wondering, will I get this table for my final exam? The answer is a big no, okay? You'll get a big no. This is kind of like Dr. Diaz refers to this as training wheels. You know, you'll use it for your first exam with molecular geometry, and you won't use it past that. Violet asks a question about this molecule here, the phosgene molecule. In this case, okay, since there are no lone pairs on the central atom, both the electron geometry and the molecular geometry are trigonal planar. Yeah, I might have forgotten to say that, but there we go. All righty. Anyhow, so it might be a good idea to print this out. In fact, let me make this available to you guys right now. So if I'm on Canvas right now, so, and don't worry about doing this immediately. But I'm making the handout for exam 2. I'm publishing it right now so that everybody can print it out. You'll see some things in there that you've learned, some things you haven't learned yet. But anyhow, you will get this table. All right. Anyhow, we've already done Pf3. We did phosgene. Who wants to try some more? Just me? No. Everybody. What should we do here? Let's do this one. SBF5. Who wants to try SBF5? That's Antimony Pentafluoride. Antimony Pentafluoride. You know what? First thing I'm going to ask my students to do is tally up the total number of electrons in Antimony Pentafluoride. I'll give you a second. Whoever can come up with the answer, I would appreciate that. Oh, good. Somebody says 40. Yeah, the answer is 40. Antimony is in group 5, so it's got a total of 5 valence electrons. And then we've got 7 valence electrons for each fluorine times 5. So that's 5 plus 35, which gives us 40 valence electrons. Let's just start like this. We know that fluorine can only ever have a single bond with 3 lone pairs. Okay, that's a rule. And so we'll start by putting our antimony like this, and we'll just draw 1, 2, 3, 4, 5 lines like this. Okay, it's kind of a quick and dirty Lewis structure, but hey, this is the land of the free. Okay, so I'm just going to start throwing on electrons onto my fluorines. I'll let the chips fall where they may. And then if I have to massage this into something a little bit more accurate, I'll do it. But I have another question for my students. How many electrons have I used up in this Lewis structure? Yeah, absolutely. I've used up all of my electrons. I've used up 40 electrons. So there's nothing wrong with this Lewis structure. I give it the double check mark, okay? Nothing wrong with that, okay? But how many regions of electron density are there around the antimony? 1, 2, 3, 4, 5. Can anybody tell me, and I know this is not easy, but I want to know if anybody could tell me what molecular geometry would antimony pentafluoride adopt? You should be able to tell me based off of what we looked at. You got 5 regions of electron density around the antimony. If you don't spell it correctly, I don't care. As long as I understand what the heck you're saying, good enough for me. Anyone? No, it's not going to be octahedral, because for an octahedron, you have to have 6 regions of electron density. Yes, it would be the Trigonal Bipyramid or Trigonal Bipyramidal. Absolutely. So let's draw that. So we've got our antimony as a central atom. We're going to draw the 2 axial fluorines first. We're going to put them in the plane of the board or the plane of the page, whatever. We're going to put one of those fluorines that's equatorial in the plane. And I'm going to have one of them going behind the page on a dash like this. And I'm going to have the other one coming out like this. Okay, so my electron geometry and my molecular geometry in this molecule is trigonal bipyramidal. All right, and of course they're always going to be the same when there's no lone pairs on that central atom. Okay, does everybody follow me on the dashes and wedges? Is there any clarification needed on that? Because we use them. You're going to have to practice them, but we do use them a lot in this class. Okay, what time is it? Oh, we got lots of time. Let's try another one. Do I give myself space? Doesn't seem like the kind of thing I would do, does it? Do we have enough room here to try BRF5? Yeah, I think we do. So Bromine Pentafluoride. I'm going to give you a second to look at it yourselves and see if you can draw a Lewis structure, and then make a decision about reds, and then make a decision about electron geometry, and then finally make a decision about molecular geometry. Does anybody have an idea about electron geometry here or molecular geometry? I'll take it, whatever you got. No takers? Okay, let's give it a try as a group. Electron geometry is octahedral. Yes. Okay, that sounds good to me. We know that bromine and fluorine are both in group 7A. They both have 7 valence electrons. There's a total of 6 atoms. So 7 times 6 gives me 42. So I've got a total of 42 electrons like that. So let's just start by drawing bromine. We'll draw 1, 2, 3, 4, 5 bonds to fluorine like this. 1, 2, 3, 4, 5, 6, 1. There we go. All my lone pairs are in. So far in this Lewis structure that I have drawn here, I've used up a total of 40 electrons. That means I've got 2 more electrons. Fluorine cannot take on any more electrons, right? Fluorine always has, it's a rule, always a single bond and 3 lone pairs. And so that last lone pair is going to go on the bromine. Bromine is in the 4th period, so bromine can exceed its octet. Okay, now how many regions of electron density are around the bromine? Let's count. 1, 2, 3, 4, 5, 6. If I have 6 regions of electron density, 6 regions of electron density, that means that all of those groups, those electrons, electron groups, whether they're bonds or the lone pair, they're going to spread out as far as possible to give me an octahedral electron geometry. Okay, let's draw what that would look like. And if you're not sure, I can help you out. We'll put the bromine in the center. I'm going to put a fluorine up at the top, like this. 2 of the fluorines will be going in the back, like that. Okay, we'll fill up their octets, lone pairs. I have 2 fluorines coming out in the front, like that. Another one there, another one here. That. In that last lone pair, I'm going to draw it at the end of a stick, like this, okay? So there we have it. So my electron geometry is octahedral. Okay, but since I removed one of those lone pairs and put it down here, what's my molecular geometry? My molecular geometry only considers the bonds 1, 2, 3, 4, 5, okay, that are derived from this octahedral electron geometry, and so it's going to be square, square, pyramidal, like that. All right, here we go. 10:33. Keep blasting here. I'll just stop for a second and just kind of comment on where we are. Look, I know I sound like a dad sometimes with my students, but I am a dad. I'm going to have another baby in a few days, and so look, you're gonna have to study. Okay, that's a pretty blunt way of putting it, and it might sound silly. I'm sure that most of you are hearing my voice and saying, "Look, Mr. Dean, I'm already working hard enough, man. I'm already studying enough." But I would say I've never seen this subject come to somebody in a short period of time. Okay, you're going to have to sit down, try some practice problems from the book, the ones that have the A icon next to them, okay, and give those a shot. Of course, we're going to do as many practice problems as we can in class. We're going to go over the practice exam, of course, yes, very important, but it always takes a little bit of time for students to master this. I also want to remind you that in order for you to be able to master molecular geometry, you've got to have mastered Lewis structures, right? That was the first thing I said in class today. And what you're going to find is that when we start looking at polarity of molecules, and that's going to be next class, you have to understand not only Lewis structures, but molecular geometry. So you have to tie those two concepts together in order to get to polarity. Okay? Okay. Well, let's keep moving. And that's the solution worked out. And I want to take a look at tetrahedral shapes around central atoms in the overall shapes of ethane and ethanol. This is ethane on the left here. So this is ethane, and this is ethanol, like that. And I want to make a model of ethane for you and show you something. I promise that for the rest of the semester, I don't think I'm going to do as much switching around in one lecture, screen to screen. Sorry, I'm just building my ethane molecule right now. So I need a couple of carbon atoms, 2 carbon atoms, because the formula is C2H6. So I've got C2H2. I need 2 more bonds and 2 more hydrogens. Excuse me. There we go. So I'm just working on it here. Okay, now hopefully you can see my screen and maybe look at your slide at the same time, but anyhow, it's not important. Here's the model of C2H6. Okay, I've got 2 carbons in the molecule. Both of those carbons have tetrahedral molecular geometries and electron geometries, right? They're attached to 1, 2, 3, 4 atoms, right? The 4th atom here is a carbon, not a hydrogen. But you can see that this carbon is also tetrahedral. So all of the bond angles in ethane are all 109.5 degrees. Give me a thumbs up if you follow me on that. Just that far. C2H6. It's like 2 tetrahedrons stuck together. Okay, cool. All right. Now, the way that I have it, the way that I'm holding it in my hand like this is called a conformation. If you're like, what's a conformation? Well, around a single bond, single bonds can rotate. Right? If I have a single bond, you see how it's spinning here in my hand? And this is reality because single bonds can rotate. We don't worry about this, rotation here because it doesn't change anything. It doesn't look different. But if I hold my ethane molecule like this, okay, where all of the carbon-hydrogen bonds are blocking each other, we call that an eclipsed conformation, right? Just like an eclipse where the moon blocks out the sun. So they're blocking each other out. Now, you can probably guess that that is not energetically preferred. Now, if you're wondering, well, why would that be? Because remember, there's a pair of electrons here and there's a pair of electrons here. They want to get it as far away from each other as possible. And so they adopt this kind of conformation where they maximize all the space in between them. And this is called a staggered conformation. And that's what's shown in the slide that I have, okay, is a staggered conformation. It's kind of like 2 tetrahedra, which is the plural of tetrahedron, 2 tetrahedra that are, offset, okay? Let me go back to my slide. Go. Yeah, and you can see how the ethane molecule, when you maximize the distance, right, when you have that staggered conformation that I just explained, it's kind of like you have a tetrahedron here and a tetrahedron here, and they're offset, okay? If you make a model of ethanol, which is where you replace one of the hydrogens with an oxygen and then a hydrogen, you'll see it's like when they maximize their distance between all of the atoms, it's like you have 1, 2, 3 kind of tetrahedra with respect to your electron geometries, okay? Because again, all atoms, all regions of electron density, all they want to do is maximize their distance, right? I'm trying to treat this lecture like an episode of Seinfeld, like tie it all up at the end, bring it back to the first thing that we talked about. Give me a thumbs up if you follow me on just regions of electron density. They want to maximize their space in between them. This is where molecular geometries come from, all these different shapes that we looked at. If you're wondering about that table or what you're going to be able to bring into exam 2, I've made it public so you can see that on Canvas now. And so what we're going to talk about next class is we're going to start by looking at some problems. And I just want to put this bug in your ear that I have a bunch of problems, I think, at the end here. I put on some problems. Yeah, there's some problems here. So if I can make a recommendation to all of my students would be to be sure to take a look at all of the remainder of the slides that are in this slide deck. Okay, you've got, some time before Friday. Look over all those and try all of the practice problems. Not some of them. Give them all a shot. And that way, when you come to class on Friday, it'll just be able to cement, your knowledge of what you've worked so hard for already. Okay, we're almost finished the 7th week of school. Okay, December is coming. All right, I don't want to wish my life away or anything, but anyhow, okay. Well, it's been a slice.